Hello, and welcome to the first video of Homework 1 for our class Computational Methods taught by Professor Ko. What we're going to be doing today is, as you can see, there's some code on the screen already, and that's because this is a re-record of Homework 1, Part 1. This homework covers vectorization, plotting. Obviously, plotting is something we've already covered in previous classes, but obviously it's still fairly important. Also, the Frenet-Serre framework, as well as Jacobians and gradients, and then 3D pipe infrastructure, I guess, is kind of a fun way to put it, because that's what we're going to end up making in videos 2, 3, and 4 as we dive into the actual mechanics. This one is more of an intro to what Jacobians are, for anyone who hasn't gotten into multivariable calculus yet. And as I said previously already, this is a re-recording. We went over this in class several weeks ago, and realized there was a mistake in what we were taught, so we went back and had to kind of redo it. So I had recorded my video before that mistake was caught, unfortunately. So that's why I have all of this code right here already written. This is just a quick, if you watch in 0.25 speed, you might be able to catch a glimpse of what we're doing in the later videos, but I'll leave that to your imagination because I'm going to start right from the beginning and redo what we did before. So what exactly we're doing is we're going to create a curve in three-dimensional space, and then using a bunch of tricks again in the later videos, we're going to end up plotting that in 3D, and then designing a frame of reference relative to where we are on that curve, so that way we can draw shapes, specifically a circular cylindrical tube, around the first curve we created. But this video isn't really about any of that. This video is focusing on Jacobians, what they are, and how we can calculate them manually, as we're going to be doing today, and then comparing them to the actual calculations that JAX does. Now, JAX is a tool we haven't used before in previous classes. It is written by Google. It's a billion-dollar Google programming platform written in Python, which is really good for artificial intelligence, networking. Networking is in like computational, mathematical networking, learning algorithms and that sort of thing. So it uses a lot of TensorFlow. So that's going to be what we're comparing against, because that definitely does Jacobians really, really well. So let's start off by, again, as per usual, importing NumPy and Python. My runtime apparently disconnected, but it's reconnecting, hopefully. There it is, it's good. So we're going to start by doing the classic of importing NumPy as NP. And the next thing we're going to do is we're going to import JAX, J-A-X. Okay, just JAX for now. It also knew that from jax.config, we were going to import config, and then config, and then from there we are going to do config dot what is it? It is update, config.update, and we're going to set jax underscore enable. It was the thing that popped up before. Jax enable underscore x64, I believe. I believe that was what it was. Jax enable 64 equal to true. I think that's correct. I'm going to run this just to see if that's... It said it was fine. So hopefully that has in fact enabled jax64. I'm going to cheat a little bit quickly and quickly scroll up to make sure I got that correctly. Jax enable times 64 set to true. Okay. Just double checking. I don't want to really go off any of my previous work because that's cheating, but I did already record that video. From the way I'm thinking about it right now, I'm still going to post that as like homework 1 part 0 kind of thing, just so you have that as a reference, because it was, still a long video and recording and effort that I went through. So even if I can't really use that anymore as the final product, I still want that, work shown somewhere. And the final thing, we're not going to need to plot anything, but the final thing I'm going to do is I'm going to import jax.numpy as JNP. Because again, NumPy, you all know what NumPy is, it's numerical Python. JAX is its own version of NumPy, known as JNP. And the reason they have that is because since JAX works with functions on like a decompositional level, right, when you're taking the Jacobian, which I probably should explain, but when you're taking the Jacobian and the gradient and the derivative, you have to break apart the functions a little bit. And so if they're containing something with NP, it's not guaranteed that the NumPy functions will be compatible with whatever JAX is doing. So JAX basically made their own version of NumPy that they guarantee works with all the JAX functions, but it functions pretty much the same way And as far as typing syntax goes, it's almost identical. It's just jnp dot whatever you're doing instead of np dot whatever you're doing. So I'm going to run that again to make sure we have jax.numpy saved as jnp, and we're going to get started. So the curve we're looking at, first we should probably define. I'm going to write it in the same way I wrote it in my previous iteration of this video. So we're going to define a function that is our curve, and our curve is going to be a function of time, radius, and a vertical slope factor, which we're going to call mz. And all it's going to do is this function, which is our curve, is going to return, if I can spell that right, an array. And that array is going to be our x value, our y value, and our z value in space at any given time. And that obviously those three values are going to be based on both the time and the radius, which is capital R, and the vertical slope factor, mz, of our curve. So x is pretty simple. It's just going to be our radius times np dot cosine of t. Our sine is going to be the same, almost the same thing, the radius times np dot sine of t. And then our vertical, our z value is going to be mz times t. So pretty simple, pretty standard curve. That's what we did previously, except in our cases, I'm gonna copy this really quick before I do anything. In our cases, r and mz were constants that were given to us. R was 4, or R was 3. I have the homework pulled up just to make sure I don't mess up any of these constants because we're not really using them anymore. For today, the point of today is just to get the point across. And then our mz was 0.4. So this is actually what we did in our original video because we had given constant numbers for radius and our vertical slope factor. I'm going to go down here and I'm going to make curve 2 and I'm going to leave it as it was written. So with this curve 2, radius and mz can be, for example, a function of time. They can be variable in general. They could be totally random for every different time. Random for every different time wouldn't happen because then you just have a bunch of points that were connected together that had no correlation because there's no, relationship between any of the variables. But anyway, this is a more general function. I'm going to be using this to prove that my Jacobian does work as intended. So really quickly, I'm just going to write curve, because again, this is the one that will just spit out a value, curve at time 0. Well, that's going to be at at an x of 3, at a y of 0, and at a z of 0. And if I go to the curve at np dot pi times 2, so 2 pi, it's also at 3. It's at basically 0 y, which again makes sense. And then our z is 2.5, which if I were to divide, if I were to just copy this number and divide it by np dot pi times 2, make sure I'll write that in parentheses to make sure nothing else goes wrong. I guarantee you it will be 0.4. There we go. So this is obviously working as intended. This is our curve. Now what we're going to look at is curve 2, because that's going to take a time. It's going to take some radius. So again, I'll just do 3 to make it consistent. 3 dot and 0.4. And it should give us the exact same thing. See there? It's identical. Obviously, this 3 and 0.4 could be functions of time because they're variable here, but that's just what I'm going to do. So this is our curve. So what we're going to do today is we're going to take the Jacobian of that curve. Now the Jacobian is kind of like, I like to think of it as a super derivative. If a derivative is like a first degree where you have one input variable and one output variable, and you take the derivative of it, it's obviously the rate of change at a specific position in time, or on that independent variable. A gradient is if you have an input variable and you have two outputs. So that would kind of be two functions, right? So for example, if you had a function where it was the x value and the y value were both computed separately from a t, and so you kind of need to know the two-dimensional slope, which is called a gradient, which is why the whole thing's called the gradient, like the function, the act of doing it is called taking the gradient. It would essentially be the derivative in the x and the derivative of the y direction simultaneously, because, obviously if you think of being on a hill, you're not just going up and down the hill, you're also going around the circumference of the hill, to be imprecise. So that's like a kind of a two-dimensional derivative. Now, a Jacobian is like a gradient, but for any number of independent and dependent variables. So what we'd get with our regular function, if we were to take the gradient, would just be the derivative of curve, would just be the derivative, because it would essentially be an array of our x value, our derivative of our x function as a derivative of time, a derivative of our y function, so fy, as a derivative of time, and a derivative of our z function, zf, as a function of time. So this is essentially all we would get out from taking the derivative of curve as it's written right now, because these are all constant and our only independent variable is t. However, with curve 2, the Jacobian and the gradient and the derivative are not all the same thing, because here we have 3 independent variables. We have t, r, and mz. So what this becomes here is that, again, I just wrote it this way because it was easier. This would actually be a vertical column. So I'm going to quickly add 2 more comment columns right here. And I'm going to cut you, put you there, cut you, put you there, line you up with everything else. So this is what it would actually look like. It would be a vertical column of those 3. It's each of our functions with respect to the only independent variable we have. But if we were to take it as the way curve 2 is written, it would be like this. Well, we already looked at the function of x derivative of t, but we also have r, which is an independent variable. So we have to take the derivative of the x function over the derivative of r. And we'd also have to take the derivative of the x function with respect to mz, because that also can vary as we go. And so what you notice, we have to do this obviously for each of our different functions, since we have 3 of them in total in this example. This would be function of y, function of y. This is going to be function of z. What am I doing? This is the function of y. This is the other function of y. This one is a function of z. This is a function of z. So as you see in this example, because we're outputting 3 things in x, y, and z coordinate, and in curve 2 we have 3 independent variables t, r, and mz, we get a 3x3 grid. If we were to have 3 independent variables but a single function, I could do this, and that would give us what we have. But obviously, so for example, if I just wanted to know what the x value was of curve 2 based on r, t, r, and mz, this is what you'd get. And obviously, since mz doesn't even make an appearance in this equation, this thing would always just be 0. The derivative of it with respect to mz is 0. I'm going to put this back. So I'm just going to run this again to make sure everything's saved in the state it was. I don't need to have you here. I'm just going to comment you out. So anyway, this is what we want to get out, is a 3x3 or an n by n grid of all of our functions. I think it wouldn't be n by n because they're not necessarily the same. So we want a grid that has a vertical height, like a column length, right? How many things are in this column that equals the number of functions that our curve is outputting, or our main function is outputting. So a height of a subsidiary function and a length of the independent variables. So that's what we're looking for. That's what we want to output. So we're going to do that manually using manual differentiation, and we're going to use a coding technique called enclosement, or not. Not enclosement, closure, which is the act of defining a function inside of a larger function and spitting out that interior function to then use in your actual coding practice. So what we're going to do is we're going to define a function, and we're going to call it get Jacob. I'm going to call it get real Jacob, because I think in my previous one I called it get Jacob, and since technically that wasn't really the Jacobian because we only were doing it with t, I took a couple of liberties and shortcuts with that one, so it didn't actually have to return anything. So what this is going to take in is some function, and using the function I give it, whatever function I'm looking at, I'm going to define a new function, which I'm just going to call jack, which is the Jacobian, and that's going to return. Obviously, we're going to want to return from this interior function. We're going to want to return a Jacobian, which I'm just going to call Jacob. I called it Jacob Maker in the previous one. I don't want to return Jacob Maker. And what we're going to do is we're going to return the function jack. So this is going to kind of be the net flow of our function. We're going to give it some function. Using that function, we're going to define the Jacobian function for that specific function, which returns the actual Jacobian array, and then we're just going to output the Jacobian function we defined. So a bit confusing to say out loud, but we're just going to continue moving on. So what is this Jacobian function that we're generating within our getRealJacob function going to take in? Well, it's obviously going to have to take in some initial position, x0, And it's going to have to take in, since we're doing this numerically, it's a numerical derivative, we're going to need some kind of dx, which I'm just going to set, I'm going to give a default value so I don't have to type it in all the time, as 1 to the negative times 10 to the negative 8th, because that's pretty small, but not crazy small, and some x0. So again, an x0 is going to be an array of all of our independent variables, right? So if we're using curve, it would just be a single value of t. If it were curve 2, it'd be a value of t, r, and mz. So it's an array, and we have to remember that as we go and work through this. So we want to make sure that, because we're going to be using the size of this array, because it could either be an array of one item up to infinitely many variables, there's also a possibility that if it's 1, they were to enter in just a float number. Like they would just put in 3 or 3.0, which is different from an array that only contains 3 in it. And because we're going to need to know how many independent variables are in x0, we're going to have to make sure that x0 is an array. So we're just going to redefine x0 as being equal to a function called np dot at least 1d of x0, which is essentially, I'm going to put a bunch of space down here so I have room, which is essentially going to make sure that whatever we put into x0 is at least a one-dimensional np array. So again, if someone types in 3.0 to curve, to our standard, I'm going to call this curve 1 just to make sure, so I can call it curve 1 and curve 2. If someone puts in just a 3.0 to curve 1, this will make sure it's 3.0 inside of an np array, which we can still take the size of and know how many items we have. We'll just be working with 1. Obviously, if we're putting these in, we'd have to put them in an array, because you can't put, this only accepts, 1 x0 and a dx, so you couldn't put in 3 variables by themselves as floats, because it would go, hey, you gave me an extra thing I don't know what to do with. So we can kind of just make sure that it's an array. And now, because we're calculating the derivative of each individual component function with respect to each individual independent variable, we need to know kind of what the ground state is. So what is, the derivative is f of x plus h minus f of x divided by h. So we need to know what f0 is, what the default value is. So that's going to do np dot at least 1d, and what we're going to put in here is just going to be the function that we passed into getRealJacob, so func, with x0. But we have to remember, as I said before, that x0 is an array. Now that we've made sure it's an array with this line right here, it's definitely an array of independent variables. And since an array is in itself an item, if we were to say this, this would try to pass curve 1 an array that contains just our 1 time, which would work totally fine. But if we're looking at curve 2, this thing takes 3 variables, and we've only passed it. This thing takes 3 arguments, a t, an r, and an mz. And right now we've just passed it x0, which in our heads is an array that contains 3 values, the t, the r, and the mz. But the way we've written it right now is just passing that array of 3 floats as t, and there's no r or mz the way it's written, because we want each item in x0 to be considered an argument. So all we're going to do really quickly is we're going to do a little asterisk here, which basically tells it to unpack x0. So it's saying each float in the array of x0 needs to be taken as one of the independent variables for curve 2. So that will just make sure we don't crash immediately when we try to run this. So now that we have our starting coordinates, or our starting point, our starting independent variables, and our ending components, because again we're dealing with x, y, z components, now we need to loop through and take the derivative for each of these columns, right? Because we're going to do it with respect to each variable at once, because if you think about it, when we run a function at all, no matter what, we're going to get it. The function of x, the function of y, and the function of z. That's what it outputs. It outputs that vertical column as a whole. So all we need to do is vary. We already have f of 0, so we already have that vertical column when nothing's been changed. So all we have to do is deviate either whatever independent variable we're looking at, t, r, or mz. I put mxz. What does that even mean? It's mz. My apologies. And we're going to need to vary that independent variable by a smidge, and then see how that affects the result. And again, dividing it by h, it's a derivative. So what we're going to do is we're going to use a for loop here. So we're going to for I in, which one are we going to look at, right? So when I said we're iterating over the columns, what does that mean? Well, we're iterating over the number of independent variables, because the number of functions just tells us how many values we're getting it out, right? The size of the array that running curve 2 or curve 1 would give us. But the independent variables is the part that we actually really care about, because we do them in batches of all the functions at once. So we're going to do x0 dot size. We're going to do one of the range, in range of x0 dot size. So what this is going to do is going to say for every single independent variable we put in the array that we've made right here, do it that many times, and we're going to calculate the columns. So what are we going to need to do? Well, we're going to need to figure out, obviously, what our new value of x is. So we're going to need to have an x plus h, which is just going to be, well, if you think about it, right, we're only changing one of our independent variables. And x0 has all of our independent variables here. So we're going to do it x0 of I plus dx, right? Because we're going to take whichever, whichever specific independent variable we're looking at right now, because that's denoted by I. I indicates which independent variable we're looking at. So we're going to take that independent variable and increment it by dx. That'll give us our new x plus h. But you'll notice here that the way this is written is this is pulling out a specific float, and this is pulling out, and this is adding a small number to it, and that's assigning it. So x plus h is just a single float. It's no longer an array of variables, of independent variables. So we cannot just do we can't just do f plus h is equal to func of x plus h, because again, our function is expecting an array of variables, right? For curve 2, it's expecting an array of 3 variables, and right now x plus h is simply a single one it's the independent variable we're changing plus h right now. So this is not how we want to write this. So we're going to have to do a little bit more, and it's going to have to do with how NumPy works. So what we're going to want to do is we're going to want a new array that's exactly like x0 that we can add dx to that specific independent variable and then use that new array. So we're going to create a new array. We're just going to call this x plus h. So x plus h is going to be equal to a copy of x0, right? Because that's the easiest way to make an array of all of the independent variables that we're basing everything off of, because that's what x0 is. So we're going to do an np.copy of x0. And the reason we're doing this and not just saying x plus h is equal to x plus 0 is because of the way NumPy works. When they're expecting, because again, this is used for really, really large computer level data sets, there's millions and millions of them. If you're referencing a specific portion, you don't want to talk about, you don't want to actually have to save an additional copy of that in memory. You'll just reference it. But np copy does make an additional copy, because if we didn't make a copy and we just referenced it and then we changed x plus h, it would change x plus 0 or x0 as well, and we don't want that. So we want to make sure that x plus h and x0 are fully independent arrays. So now that x plus h actually represents a whole array, we want to make sure that we're only changing the one value of the array by taking x plus h of I, right? So the specific x plus I we're looking at, and making it, and this could also be x plus I. I'll do that here. I'll leave it like this, actually, because again, x plus 0, we just described that x plus h is exactly x plus 0 at this moment. I'll change it just in case. I'm not 100% sure how. I think it should just return a float and increment it and then set it there, but just to be safe, we're going to put x plus h. So again, it's going to take the value of x plus h at I, which is equal to x plus 0, add our dx to it, and put it back in. So now our x plus h has been varied according to the only independent variable we're talking about at this moment, and now we're going to run the function of x plus h. Again, x plus h is an array, so we're going to need to unpack that to make sure it knows that each item in this array is one of the variables in our function, and this should work. So now we have our value of our new array, our new column that shows us what the function, what the new value of our functions are, each of our component functions, after they've been adjusted. So now what I'm going to call delta is just going to be, the derivative, which is going to be f plus h minus f of 0, because again, f of 0 is our whole thing right there. So that the difference between them, and then we're just going to divide it by dx. This right here is the amount that we were changing. And again, because this is an array and this is an array, we can subtract them, and it's going to subtract each item from each corresponding item in the array and then divide them all. So we're still getting an array out here. Delta is an array. I'm going to write that here just to be sure. Delta is an array, just to make sure we understand. And I'm going to right here put in comments to unpack the x0 array. And I'm going to put that, copy that down here, make sure I know x the x plus h array, x plus array. So now we have all of our differences. So we now have the delta columns right here, right, for one of our independent variables. So now what we want to do is we want to, as I said, we don't want to spit these all out sequentially. We want to spit them out as a single thing. So I said we're going to return Jacob, right? So what exactly is Jacob? Well, the Jacob is going to be an array that constitutes all of these different delta slices, right? Because each slice is a column, so we want to make sure that they're all being put together. So what we're going to do is we're going to define Jacob outside of our for loop and then append everything in the for loop to that. So we're going to create Jacob. It's going to be equal to, easiest thing we can do is just make a big array that's as big as we want, or as big as we're expecting it to be, of zeros. So how do we do that? Well, we're going to do np.zeros, and that's going to give us an array full of exclusively zeros, and we're going to put in the size of that. So how big do we want this array to be? Well, as I said before, it depends on the amount of independent variables, which represents the number of columns, so our row size right here. So we have 3 independent variables, t, r, and mz. So we have dx, or dt, dr, and dmz. So that's going to be the length of our array. That's going to come second, and what's going to come first is our vertical part, which again is the columns that we're spitting out every time. That's going to be just however many independent variables we have. So that comes first. So x0.size tells us how many variables we have, how many independent variables we have, as we said earlier. And again, because we've made sure x0 is at least one-dimensional, we are allowed to take the size. And then this one is going to be f0.size, because this is going to represent the horizontal part of our array, which is the number of, I flip these around. First comes the vertical part, which is again our f0.size, because that tells us how many component functions we have inside of our main function func. And the latter part is going to be x0.size, because that's going to tell us horizontally what we have, which is our independent variables. So again, dr, dz, dt, dr, and dmz, the band. So now that we have our Jacob, and it's a big grid of zeros that are the correct size, how do we make sure that we're appending our delta to Jacob? Well, it's actually pretty simple. We have to remember our delta is a 1D array, I'll put it right here, 1D array, and Jacob is a 2D array. So I'm just going to put 2D array right here so we can make sure we remember that. So what we're going to do is we're going to append delta to that specific column in Jacob we're interested in. So we're going to take Jacob, right? And we only want to look at one column. So we want to look at every single value in the certain column, and we want that column to be column I. Because again, if you remember, this I represents the the index of the specific independent variable we're looking at for this iteration of the for loop. So we want to look at that specific, so again, we're starting off with T for the example of curve 2. We want to look at the column that T is in, which is going to be column 0. And we want to look at every single value in that list. And we want that to be equal to all of the values in delta, right? So we just want to put is equal to delta. Right? So we're done now, correct? And you'd be wrong. Because again, as I said before, delta is a one-dimensional array. And this right here is a two-dimensional array, which means delta is linear, right? Delta looks like this right now, right? Delta is a x, y, z, g, h, f kind of thing. This is what it looks like. And again, Jacob we want it to look like this up here. And what we want to do is we want to make sure that each one of these values, x, y, and z, becomes stacked vertically like this. And we don't need to use a stack function for this. We can actually just decompose this in a certain way. So what we're going to do is we're going to slice this as well, and we're going to treat delta as if it were a two-dimensional array that only has one column. So what we're going to do is we're going to slice it and say all of the values in the first column, and we're going to say that column is going to be 0. So what this is going to say is that it's going to treat all of, I think this has to be none, I think. Because we want every single value in delta to become the vertical portion, but we don't because we're treating it as 1. So I think this will be 0. If this goes wrong, it could be none. I'm kind of flip-flopping back and forth in my head because I'm thinking of broadcasting simultaneously, and broadcasting and kind of up dimensioning an array are kind of similar in the fact they both kind of use imaginary axes that aren't actually in the variable, but by treating them like they are there, you can pull information out and extract them in a way that's helpful. So I believe this will work. So I'll run this, see if it doesn't give me any syntax errors. So that's not really a guarantee, but I'm pretty sure this should work. So to check, we're going to run curve1 first, because curve1 only has t. So we're going to do curve underscore jack is going to be equal to get underscore real Jacob of curve1. I run this, and it said it executed properly. So now what we're going to do is we're going to take curve underscore jack, and we're going to want to evaluate it at a certain time. So our time is going to be, I'm going to prove that we can just throw in a float. We're going to just do 0 dot. So we're going to look at the time 0. Too many indices, arrays, one dimensional. Okay, so that doesn't work. So maybe it is just delta. I'll try this again, try u, works. Now I'll try. Okay, so it is just delta. Never mind. I was thinking of broadcasting then in that case. So here we go. So if we look at our Jacobian at time 0, if we look at our curve at time 0, the change in the x is 0, which makes sense because if you think about this way back up here to the curve, it's cosine, the derivative of cosine is negative sine, and the negative sign of 0 is going to be negative 0, which is just 0. So that's fine. The derivative here is going to be 3, because the derivative of sine, obviously, again, is the derivative for this one, is 3 times sine. Well, the derivative of sine is cosine, so 3 times cosine. Cosine at 0 is 1, so the derivative makes it 3. And 0.4, since it's relative to p, is literally just a constant, so 0.4 is always going to be the slope of the z, the z incrementing, and that's why it's mz, is it's the vertical, the z-axis slope, essentially. So that makes sense. And again, as we said before, we got a vertical array. So that's good. If we want to check at np dot pi times 2, we could run that, and we'd see that, again, if you can think about it coming full circle, we'd be exactly where we started position-wise. And again, our slope would be about 0, because again, we're at the same point, so it should be about the same. So 0, 3, and 0.4 matches up. Makes sense. Now that's exactly what I did in my previous iteration, in my previous video, which I'll show really quickly up here. This thing did exactly the same thing right here, but it was way simpler. It was a single line and really didn't even need to be like super confusing, but that's because it just took the derivative, essentially, or the gradient maybe, but again, for a single input function, the derivative, the gradient, and the Jacobian are all the same, because it's just, there's only one input variable. There's only one thing according to which it changes. So now what's really going to make this interesting is if we use curve 2, because curve 2 will tell us if this really is an accurate Jacobian function, because now radius and our vertical slope factor can both change as well. So the definition stays the same. We're going to create this again. So it took a little bit longer because it had to run through this for 3 times instead of just once. And now we're going to run this at 0 as well. So 0. Let's see if this works. Curve 2 is issuing 2 positional arguments, r and mz. Okay. What do you mean? I unpacked it. So if I get rid of that, oh no, okay, wait, hold on. I just realized. I was taking the curve 2 and was just using plus 0. I don't even think any of that was this. I don't think okay, wow. Wow, I'm stupid. Okay. Let's get back to this. So, we're going to put in a list here. Wow, I'm stupid. Okay, incredible. All right, so I didn't pass an array of the correct number of sizes. So I'm going to have to fast forward through that so fast. That's really embarrassing. That's totally on me. Okay, so we're looking at a time of 0, and just to make it match what we did before, we're going to have a radius of 3 and a r of 0.4. So this, redefine u, this should run. There we go. So the unpacking did in fact work. I just needed to actually put in the correct number of things. So again, the reason I can put not an NP array in here and just put in a regular list is because of this at least function. But as you can see right here, this column right here should be exactly the same as what we did previously, 0, 3, and 0.4. With here, you can see that the derivative of our cosine, since with respect to r, taking the derivative of this with respect to r, well, cosine of t of 0, the cosine is going to be 1, and the derivative of r is going to be 1 times r, so it would just be 1. With here, the derivative of this with respect to r would be r times sine of t, which is 0, so the derivative of r times 0 is just going to be 0, which is what we see. And of course, m times z, same thing, t is 0 times mz. There's no r in here anyway, so it's just going to be a constant of, and the derivative of any constant is 0, so that's 0. And then when you take it with respect to mz, this has no mz in it, so it's a constant, so it's 0. This has no mz in it, it's a constant, it's 0. This does have an mz in it, it's times t, but t is 0, so it's 0 times mz. The derivative of 0 times mz is just going to be 0. That works out. But if our time were to be something that wasn't 0, like for example np dot pi times 2, well, now we get some more interesting numbers. This is again about 0, this is about 3, and this is about 0.4. Right here we see this is again approximately 1, this is approximately 0, and this is approximately 0. However, down here you see we get 0, 0, and a number that is not 0, 6.28. And if I were to copy this right here, I guarantee you if I divide this by np dot pi times 2, wrap that in parentheses of course, we're going to get 1. And if you wonder why would we get that, it's because again we're taking the derivative of mz times t with respect to mz in this column. So t is 2 pi, about 2 pi, so 2 pi times mz with the derivative of mz is just going to be 2 pi. So this is 2 pi, so I divide this by 2 pi and we get approximately 1. So it just goes to show that you can take the Jacobian now with respect to the whole thing. And obviously this is what we were supposed to do in our first video, but there was again a mistake, so we didn't truly understand what it meant to take the Jacobian relative to the gradient and relative to the derivative, because those were all equivalent for the curve we're actually told to look for, which is this. This is what we were supposed to look for. This is just my proof that what I've written right here does work for something that has multiple input variables. So again, we get a 3-sized column here, and everything works fine and dandy. So thank you very much for tuning in to this re-record of Homework 1 Part 1. I hope you enjoy the rest of our videos, which obviously I don't use this in. Oh, I forgot, I almost forgot. We have to compare this to the real answer, to jax.jacobian of curve 2, which we're going to just call curve underscore jax, because it's almost like curves.jack. We're going to run this, and then we're just going to do, I'm going to literally, I can just copy this and literally change the c to an x, and it should work. This one I need the answer as a JNP dot array, because I don't think it has a 1D context. Okay. So I guess the issue is that you had to unpack it in curve underscore jax as well. So if I just do this, will it still work? Yes. Okay. That's so annoying. And it doesn't seem to be rotated the correct way either. So we're going to do a dot t to transpose it so that it's rotated the same way. Tuple object has no attribute t. Oh, no way is this really... Okay. So I'd have to do a for each in tuple rewrite. Okay, this is really getting on my nerves. I really don't like... It's not a great sign when I prefer the one I homebrew wrote myself as compared to this one. But I'm sure this one's way better for computer science or something. But for a human being trying to just use it as a Jacobian tool, kind of sucks, and I kind of hate it. That's all right. That's fine. I'm so glad I didn't have to faff around with any of this when I was doing the rest of the homework parts, because again, the homework we used just differentiated it in terms of t. So since there's only ever one variable coming in, it was very simple. But as you can see right here, this is exactly the same. So this vertical row right here, this column is the same as this horizontal row right here. If you look 0, this is approximately 0, this is approximately 3, this is 3, this is 0.4, this is 0.4, that matches up. The next one, we have 1 and 1, essentially 0, essentially 0, 0 and 0. And then right here we have exactly 0 and 0 on the first two, and then 6.2, which again is 2 pi, and right here they match. So, as you can see, all of our answers are work. It was a bit strenuous to get it to go as jax. Kind of annoying, very annoying actually. But you know, it all works out in the end. There's going to be a lot of stuff I'm fast forwarding through. That's going to be a real pain to do in DaVinci. But anyway, I've been Ethan. You've been a great viewer. Thank you for watching. Again, we've proved that you can take the Jacobian homebrew or using jax and you'll get the same answer using this function that I've written here. Mine is a little easier to use for people, but that's okay. Jax was written by billionaire Google computer scientists, so I'm sure it's got its upsides too. But thank you for watching. I appreciate your time, and have a good evening.